Hi, welcome to the channel. Today I'm going to do a quick video on all the different differentiation tests that are out there. I'm going to look at stationary points, going to look at increasing, decreasing, maybe even convex, concave, point of inflection, all that kind of thing. So why don't we take some sort of example graph? So first thing is, let's just differentiate it before we sort of write out all the different tests, just so we've got something to play around with. Differentiating, that will go to x squared minus 4x, multiplying the 2 down, minus 5. Alright, there you go, that's a good start, successful differentiation. Let's get our first test then. First thing we need to, well, not need to, but want to analyse is when dy by dx equals 0. When the derivative equals 0, they seem to have about 14 different names they like to call this, but well, let's write a few of them. You've got turning points. Call it stationary points, right? Stationary, turning. Yeah, and another word they might use is, well, you could say like minimum or maximum. And it all means approximately the same thing anyway, and it's all going to happen when dy by dx equals 0. Why don't we just do a quick little drawing of the graph then. And I'll put it on. But actually, let's solve it first and then I'll put it on. So solving dy by dx equals 0 down here would be x squared minus 4x minus 5 equals 0. You've got your quadratic skills, you've got your quadratic knowledge. That'll factorise as x minus 5, x plus 1, I think, last time I checked anyway. So you've got x equals 5 and x equals minus 1. Pretty good. So you're going to have a turning point here and here, minus 1 and 5. All right, that's the x coordinates though. We don't, yeah. Is it down here? Is it up there? Let's find out. Let's get the y coordinates. To get the y coordinates, we've got to sub it back in to the original equation. So I'm not going to do all the working for it. Probably just going to put it in my calculator actually. Get my government approved calculator sort of ready to go. And putting in the 5, you'll have 1/3 of 5 cubed minus 2 times 5 squared minus 5 times 5 plus 15. See what we get. Minus 55 over 3. So it's about 18 or something, right? Minus 55 over 3. And for the other one, putting the minus 1 in, really enjoying every press of the calculator, you know. Just realizing that the glory of an answer is about to appear before us, like some sort of ethereal vision. 55 over 3. It's actually the positive almost version of it. Sorry, 53 over 3. 53 over 3. So you get y equals minus 55 over 3 and y equals 53 over 3. Now we can plot them. So that's actually a negative coordinate for the turning point. So that's here. And oh, sorry, it's the wrong way around. So when x is 5, you get a negative turning point, so that's somewhere down here. And when x is minus 1, you get a positive coordinate, so that's somewhere up there. Also, this is a x cubed graph, so knowing that the shape of it's a kind of an S shape, we can just sort of roughly draw this on now. Actually, another thing we could add into it is it cuts the y-axis at 15. How do I know that? X equals 0, if you put it in, you'll get 15. So I can actually add that on too. And overall, we get this kind of situation. Pretty good stuff. Pretty good stuff, I must say. Big fan of that. And I guess we could actually label this. Could call that 5 minus 55 over 3. minus 153 over 3. So that's turning points. Next, increasing and decreasing. What does that mean? Well, let's look at the graph first. You might have a bit of a visualization, or you might have a feel for what it might mean on a graph. If you're going up a roller coaster, it's increasing. If you're going down a roller coaster, it's decreasing. And then you're increasing again. So working from left to right, if it's going up, it's increasing. If it's going down, it's decreasing. So actually, just looking at that immediately, I could sort of tell you the answer for when it's increasing or decreasing. But because it's going to be before this x coordinate and after that one. But let's get the same answer using maths and using the tests. I'm just going to tell you them and then explain them. dy by dx is bigger than 0, or dy by dx is less than 0. So, okay, which one's which? Let's have a think about it. dy by dx is bigger than 0. That means the derivative is positive, and the derivative is the gradient. So where on the graph is there a positive gradient? If you drew a tangent, where would it give you a positive gradient tangent? Well, the answer is, if you drew it either kind of in this first section here or the last section. So that is for increasing. And no huge surprises then. If your derivative is negative, that means your gradient's negative. That corresponds to where the graph is decreasing. So that's your tests for increasing and decreasing. Why don't I just draw one tangent on here, just to show you what I'm talking about. Here's a little point that's just after 5, maybe it's like 6 or something like that. If you look there and you drew a tangent to the curve, that's what it would look like. It's a positive gradient tangent. So it's not always totally obvious to make that connection, right? Between why is something that's going up the way like that mean dy by dx is bigger than 0 mean increasing, putting it all together. So I'm doing what I can for you guys, but yeah, you've got to convince yourself that anywhere where it's going up, the gradient is positive, if you drew a tangent. And anywhere where it's going down, the gradient is negative. And that's what this means. Positive, bigger than 0 derivative, negative, less than 0 derivative. Okay, let's just rub that little tangent out and move on. Because we've got, that's quite good. We've got the derivative is 0, we've got the derivative is bigger than 0, derivative is less than 0. And that's first derivative. Next up is second derivative. There are some tests with that as well. So why don't we just do it actually. I'm going to write it in here. Second derivative looks to me like 2x minus 4. Yeah, just x squared goes to 2x and minus 4. X goes to minus 4. You can't go wrong with that. You can't lose, can you? So what's going on with that? Again, I'm going to write down one of the things. Well, there's one thing you might want to think about anyway, which is the comparable to here. D squared y equals dx squared equals 0. So what's the equivalent of the first derivative equaling 0 for second derivative? Well, let's solve it and then let me tell you. So if you set that equals 0, here you're really doing 2x minus 4 equals 0, which will give you x equals 2. Could get the y coordinate as well. So we just do it in a turbo manner. 1/3 times 8 minus, minus 8, oh, that's very good. Minus 10 plus 15. It's a good sort of fraction action today. You're getting all the sort of fraction skills. You get y equals minus 1/3. So that is here. think I'm not going to mess the graph up by labeling it up there, but that is when the second derivative equals 0, and it's called a point of inflection. Now, I don't know about you, I don't know if you're looking at that thinking, wow, that's a lovely looking point on that graph. Are you thinking, oh my goodness, what on earth is that? This looks, kind of looks like meaningless maybe, like how can that be of any use to man, woman or child? But there is something exciting about it, and you got another sort of 3 seconds to think about it while I write inflection a little bit more neatly, because neatness is paramount, isn't it, in day-to-day life. Okay, so that rambling bought us a couple of seconds, but now I'm telling you, think of the curvature. Imagine something's curving round this way. It's almost like curving clockwise. It's maybe how I would think about it. It's like going whoop. It's like a Loch Ness Monster type whoop. Okay, and then all of a sudden, at some point, it stops doing the whoop and starts doing the heap. All right, cat's going mad in the background, but nevertheless, whoop and weep. So it's the point of inflection is the point where the curvature changes. I might even write that as a little note. It's where curvature changes. Now, that could be a turning point, and it sometimes will be a turning point, but not in this one. I'll show you a quick example of when it could be a turning point. I'm just going to draw it here, I'm going to rub it out afterwards, but just a normal x cubed graph, for example, that does have, right at the origin 0, 0, the point of inflection, which is also a stationary point. Wow. So it stops at that moment, the curve, and also the curvature changes. You've got to be kidding me. But yeah, it's possible. But a point of inflection more generally is, it doesn't have to be a stationary point. That can be quite difficult in some of the questions when they ask you to determine the nature of a stationary point or show that it's a point of inflection, or, there could be a lot of times when you're doing either this equals 0 or that equals 0, and you want to get them mixed up, or your brain's wanting you to get these mixed up. But try and be clear about them, that there are different things. This is specifically for stationary points where the gradient is 0. Let me just be clear about that. Didn't mention it earlier, but look, that's where the gradient's 0. Same in this example, there's one point here where the gradient's 0. But a point of inflection has nothing to do with the gradient. 0. Nothing to do with the gradient. It's to do with the curvature. So you can quite happily get second derivative equals 0, which is not a maximum minimum point. Okay. And finally then, and related to that, it's probably the last main thing that we need for our classic differentiation test rules. By the way, this is all kind of AS level difficulty of the actual derivative, but when you go into A2 in your year 13, you're going to maybe do harder differentiation, but all the tests remain. They linger around like a bad smell into A2. So although the actual derivatives will get harder, you can still apply all of the tests to the harder derivatives. Come on then, let's bring this home. And it is related though. D squared y over dx squared, okay? In fact, I wrote that a little bit big, but it's going to be similar to these ones, the increasing and decreasing. We're going to do a d squared y, so second derivative is bigger than 0, and a second derivative is less than 0. And places where it's bigger than 0, that you call that concave up. Sometimes gets called convex, so maybe I should write both the things in. And this is concave down. So what do I mean by that? So shall I write the second terminology in? Second terminology is, that can be called convex sometimes. Sort of depends on your exam board, that actually. In which case this would just get called concave. Concave up, concave down, convex, concave. So for example, looking at concave up, where's our second derivative? Here it is. 2x minus 4 is bigger than 0. That means x is bigger than 2. So on this graph, concave up corresponds to when the second derivative is bigger than 0, which is when x is bigger than 2. Well, 2 is that point of inflection. So all the bits that's concave up is all this bit. It's the second part. It's when it stops, curving whoop, and starts curving he. Right? Curving up the way, it kind of makes sense, like concave up. All right? And the bit before, if you took second derivative less than 0, you'd get x less than 2, is concave down. It's curving. All right? So, if you like, second derivative 0 is the point of inflection. Before that on this graph, you've got a concave down curvature, which is second derivative less than 0. And then after that point, you've got a concave up curvature. Furniture. Something which I didn't actually do the first time, and let's just finish it off now, is draw on what the increasing and decreasing means. Then I'll just do a quick summary before finishing. Just going to draw that on again without that. Yeah, so for the increasing and decreasing, you really do need to solve a quadratic inequality. So why don't I just do it quickly down here. For example, for increasing, x squared minus 4x minus 5 is bigger than 0, would be increasing. And quadratic inequality, you should sketch the graph quickly. What came out is the thing again, yeah, x equal, we know the roots are, or the answer, the sort of roots for it are x equals 5 and x equals minus 1. Sketching this very quickly. Now I'm not sketching that graph, I'm sketching x squared minus 4x minus 5 as a positive quadratic. It just looks a bit like that. And this is minus 1 and this is 5. So where's that bigger than 0? The graph is bigger than 0 here and here. Quadratic inequality solving. X is less than minus 1 and, or you could say or, x is bigger than 5. It doesn't really matter if you say and or here, does it? That usually is quite important, but I think for this, for just getting the point across here, it's not a huge deal. So, what have I just done? I've set I've set first derivative. What have I just done? I've set first derivative bigger than 0 to find when it's increasing the graph. That's this equation. It gives you a quadratic equality in this case. I've solved it. It says x is less than minus 1 or x is bigger than 5 by solving the actual algebra of the quadratic inequality. And now I can marry that up with the picture because I already know, and so do you because we talked about it earlier, that yeah, anything less than minus 1 is where the gradient is positive, and similarly after minus 1, after 5, sorry, the gradient's also positive there. So you get positive gradients there and there. So visually from the graph you can see it, and now also in algebra from doing the dy by dx is bigger than 0 test, you can also see it. That applies to the inequalities here too. If you've got a more complicated graph, the same thing might happen. You know, it's not always going to be a quadratic here, it could be anything. But whatever it is, you've got an inequality to solve, and the answers will correspond to when, you know, the graph's increasing, decreasing, concave up, convex, whatever. as you require. So absolute turbo recap of everything then. All right, differentiation tests, you've got to know them. They come up pretty early in the AS syllabus and sometimes people have forgotten them by A2. So save this for your revision closer to the exams. And you know, that's the key point you need to get into your head. I know it's confusing. I know there's different dy's and dx's and second derivatives, and it's got to be hard to understand it or remember it, let alone understand it and visualize it. But let's go for it one time and just see if we can get it all in there. Well, this is the most important thing, right? You need a tattoo of this to sit the exam. I believe the invigilators check on entry that you've all got tattoos, because you must know that the first derivative equals 0 is a whatever word you fancy that particular day. Stationary point, turning point, minimum, maximum. That corresponds to the points on the graph where the gradient is 0. There's a maximum, there's a minimum. I might say one more thing about that actually afterwards. Next, increasing and decreasing. Well, that's when the first derivative is bigger than 0 or the first derivative is less than 0. And visually, that looks like something going up from left to right or something going down from left to right. And just make that connection if you can, that something going up is going to have a positive gradient, and that's why the derivative is bigger than 0, because the derivative is the gradient. Same with going down the way, negative gradient will mean decreasing, and that will mean dy by dx is less than 0 because the derivative is the gradiente. Next, differentiate a second time. That's what you get in this case. Who knows what you'll get? But whatever you get, you set it equal to 0, that will give you the points of inflection. It'll give you all of them. Oh, there's only one here. Look, no other solutions. You just got x equals 2. Get the y coordinate as well. There it is. Weird place. What could it mean? I'll tell you what it means. The curvature. It's not the most important thing in A level, but it certainly can come up, and get good at it while you can. That sounded quite threatening, but yeah, let's go with it. Get good at it while you can. Consider it a threat. So yeah, it's when it stops curving. Almost, I would think about it like a kind of clockwise curvature and then counterclockwise curvature. Maybe that's just my brain. You've all got your own brains. Think what you want to think. But that's what point of inflection means. It's where the curvature changes. Now that could be a stationary point. May or may not be a stationary point. All right. No guarantees on that. And you should always check these separately. And linked to that idea, if you specifically want to find out where it's curving this way as opposed to that way, i.e. where there's a curve kind of where the cavern's facing down versus the cavern's facing up, clockwise, anti-clockwise, whatever you want to call it, they call it usually concave up, concave down, then you can do second derivative bigger than 0 or second derivative less than 0 tests. Just to add on to that, something that I forgot that I probably should have mentioned, but here we go. This is a good little finale, is that it's the same tests actually for the turning points. This is where the two things kind of meet. In fact, it's going to be kind of, maybe I should write something differently. Let's say something at turning points. First derivative. Sorry, at turning points, second derivative bigger than 0 is a minimum, and second derivative less than 0 is a maximum. So yeah, that's the last thing to add to here, that for the turning points, if at the turning points the second derivative is bigger than 0, it's a minimum, and if at the turning point the second derivative is less than 0, it's a maximum. I always think about it that if it's positive, it's like a positive quadratic, positive x squared, which is like a smiley face, and a negative is like a negative quadratic, which is like a sad face. Now that's my little way of remembering it, but you can come up with your own way. This is a generalization, no other way around. This is a generalization, is that this is a special case of that. Like that's concave up everywhere after x is 2. Not only at that minimum point, not only at that point there. So yeah, you've also got this at turning points, the second derivative is bigger than 0 is a minimum, and the second derivative is less than 0 is a maximum. I kind of think about that as positive second derivative. It's like positive x squared graph, which is a smiley face. And the negative is like a negative x squared graph, so less than 0, which is like a sad face. It's my little way of remembering the minimum and maximum test. This is a special case of, this is more general, this is for all points, you know, if something's curving one way or the other way, but it has a specific result. And actually you can see what the result's going to be, right? That one is going to be a minimum, so that's when x equals 5. So I'm expecting x equals 5 is a minimum, and you're expecting x equals minus 1 is a max already, just from getting the y coordinates. We kind of know that. But if you really wanted to drill it home and check it, you could plug it into the second derivative. Shall we just do it very quickly to finish? So what have we got, for example? We've got, we put the minus in. Well look, if you put the minus in, if you put the minus 1 into the second derivative here, what do you get? D squared y over dx squared equals minus 2 minus 4 is minus 6. Check our tests. Is the derivative bigger than 0 or less than 0, the second derivative? Minus 6 is less than 0, so that means it's a maximum. And we knew that already from the picture, but again, there's two things at play here, isn't there? There's one understanding it visually from the picture, and one being able to get it directly from algebra. Quite often there won't be a picture in the question and you'll just be doing the algebra, but sometimes you might want to sketch the picture yourself if there isn't one there. It depends, are you a visual person, are you not a visual person, you know, who knows. But by the way, the actual 6 doesn't matter, for us anyway. It doesn't really matter if it's minus a million or minus a quarter. The fact it's minus is the thing that's mattering. Second derivative less than 0 is telling you it's a maximum. Cool, so okay, that's a bit of an overview then of differentiation tests. I trust you guys. Thanks for coming and watching this video, and I hope you have a lovely day.